All right, good morning, everyone. Let's get started. This is day 2 for a multiple choice test. And we're looking at page 19. All right, so starting off with number 1, we're asked to find the derivative of an integral of e to the 4x squared. So this is an example of applying second theorem. Second theorem says that rather than going through the full process of taking the definite integral and then turning around and taking the derivative, we know that we're just going to arrive back at where we came from for the most part. So we know these two operations will kind of undo and cancel each other out. We just have to worry about what happens with that process as we go back and as we go there and come back. So second theorem says the operations cancel each other out. However, the upper bound does have an impact on the answer. So we insert the upper bound into the variable. Okay, multiplied by the upper bound's derivative. So we have to go to the upper bound and find its derivative. That is the impact that's from the derivative portion of this process. So z's derivative is 1. And that's it, just e to the 4z squared. There's no plus c. Okay. All right, so again, second theorem says take the upper bound, insert into the variable of the original function, and then multiply it by the upper bound's derivative. P becomes P prime. All right, questions with 1? All right, number 2, if the definite integral from 0 to 2 of the expression is equal to 12, then k must be. I think the way we can do this is let's pretend like we don't see the 12, okay? And let's just see how far we can get with that expression. Okay. We're trying to solve for k. First thing we do is when we see a definite integral is we ignore the bounds, right? We just worry about taking the antiderivative of the expression that we see inside. I'm going to handle this portion here. All right, so every term is set up nicely for power rule. We'll treat k like a constant. Okay, so 2x cubed becomes 2x to the 4th over 4. Kx squared becomes k stays. X squared becomes x cubed over 3. And careful, this doesn't become 2k squared over 2. Again, k is the constant. So the integral will just be 2kx. Right? Imagine if it was just like 4. 4 becomes 4x. 2k will become 2kx. All right, we're making a constant rise up to a degree 1. All right, every degree is going to rise 3 to 4, 2 to 3, and this is really sitting at degree 0. Degree 0 will rise up to a degree 1. All right, once we have our antiderivative, we can now work in the bounds. Okay. Upper bound first, we can reduce to be 1/2 here. All right, so upper bound, 2 in for x. 2 cubed plus 2k times 2. Minus, okay, now we're ready for lower bound, 0 and for all the x's, but we see that 0 is just going to wipe everything out in this case. Right, let's clean this up. We know that all this is a result of the left side of this equation. And we can set this equal to 12, and that will allow us to work and solve for k here. To the fourth is 16 over 2. Do some common denominator here. Okay, combine line terms, 12 minus 8 is 4. All right, so we can solve for k here. If I cross multiply, I'll multiply the 3 over to the other side, 4k equals 12. Divide both sides by 4, k equals 3. Okay, number 3, indefinite integral. First thing we do is, can we rely on power rule? Okay, so it looks like power rule is not going to be able to get us there. There's too many terms in the denominator. Next step is, well, it's a u substitution. And looks like u substitution is going to be a good fit. If we let the u value be the entire denominator, the derivative should handle nicely with the top. Make the x's go away, pull the 1/2 out in front. Okay. So we recognize this as natural log, right? If that u was any other power, we would force it up and go through power rule. But this is u to the first power in the denominator. We have a special rule for this, natural log. So we take care of the calculus. The integral of 1 over u is natural log absolute value of u. Integral notation drops out, du drops out. In place of it, we have a plus c. So this is our calculus step there. And then from here, we're just trying to clean up. Bring the u back in terms of x. All right, page 20. Any questions? Okay, base of a solid is a region in the first quadrant bounded by the x-axis, y-axis, and the curve x squared plus 2y equals 4. If the cross-section of the solid perpendicular to the x-axis are squares, find the volume of the solid. Okay, so this is volume with cross-section here. Let's figure out what this graph looks like. Let's solve for y, just kind of give some idea here. So Subtract x squared from both sides. Divide both sides by 2. Okay, rearrange it. I can pull that -1/2 in front. Just feels more recognizable if I write it this way. So this is really a parabola, x squared, that's parabola, that opens down with a y-intercept of 2. Okay, but we want this parabola, the shaded region is going to be bounded by the x-axis and the y-axis, so in the first quadrant, so it's going to be this kind of this quarter circle looking shape here. All right, no rotation here. We're building squares on top of this base, but we always have to draw our base length, right? We got to figure out which direction to draw our base length. We want the base to be perpendicular to the x-axis. So x-axis is this way, horizontal. Perpendicular would make it vertical. So vertical base. So our base is going to be top minus bottom. The top of my base length is touching the curve, and the curve is defined as -1/2 x squared plus 2. Minus bottom. All right, top minus bottom. Bottom of my base length is touching the x-axis, which is an equation of y equals 0. Okay. The area formula for square is base squared. And now we can give it that third dimension with the integral once I insert that in. No pi in front, right? We're not building circles. We're not rotating. So this is not this method or washer method. We don't have a pi in front, just the integral of the area. Okay, this is meant to be a calculator question. We can enter this into our calculator. Okay, questions with 4. All right, number 5, function f is continuous on the closed interval from 1 to 5. Values are shown. The values in the table are used to calculate a trapezoidal sum. What's the approximate value? So we're going from 1 to 5. We want to use all the subintervals that's provided, and we're going to go through area formula for trapezoid. So 1/2 width, height 1 plus height 2. Okay, so first, let me identify all the value of all the widths. 2 minus 1 is 1, 3 minus 2 is 1, 4 minus 3 is 1, 5 minus 4 is 1. Okay, so once we have that, we know that all the width is going to come from these values that we just found. Okay, that's the width information. and then the height information is going to come from the f of x. Okay, so those are the numbers that we're pairing together. I saw on the last quiz where students were using the width here and then finding the height among the x's. Okay, so once you find the width, then it can ignore that first row. This first row is not going to be used anymore. We're using the top, each of the subtracted values of each of the subintervals will be your width, and then your height will be the bottom row. All right, so we have to do this 4 times. We have 4 subintervals, so we're going to be dealing with 4 trapezoids. First trapezoid, 1/2 width, height 1 plus height 2. Second trapezoid, 1/2 width, height 1 plus height 2. Keep going down the line. Third trapezoid. Okay, we just add all this up. 7/2, 10/2, 8/2, 4/2, 14.5. Right, number 6. If uppercase f of x is the antiderivative of lowercase f of x, so just to kind of build that relationship here, we know that uppercase f is the antiderivative, the integral of lowercase f. Okay, so if we establish that relationship, we understand that this lowercase f is really not at the same level as uppercase f, right? It needs the help of integral to make it even rise to the same level. So what that means is we know lowercase f is sitting down here. It's sitting at the derivative level of uppercase f because it takes the integral of lowercase f to bring it up to the same level. Okay. So we know that uppercase f prime must be equal to f of x. Okay, so we understand that this lowercase f is really at the derivative level of uppercase f. Okay, so we're given basically the derivative function. We have a anchor point, and we're looking for a final point. So whenever I see this, I'm always thinking, okay, this is a final equals initial plus displacement. I can think of it as a almost kind of force it into a particle motion problem, particle motion formula. All right, we've worked with this formula a lot here. That states x of b equals x of a plus the definite integral from a to b of x prime. All right, we can adapt it for our problem here. I'm looking for uppercase f of 2. I have uppercase f of 0. I want to figure out how much distance is covered between these 2 points. So bridging that gap between 0 and 2, and I have my f prime to tell me how much progress I made between the starting point and the ending point. I'll add these together and that'll give me uppercase f of 2. F of 0 is 1. We use our calculator, definite integral from 0 to 2, square root of 4x plus 1. All right, number 7. Okay, uppercase f and lowercase f are continuous. Uppercase f prime equals f of x, so we know that this f is really at the f prime level. Okay, we want to find the definite integral of f of 3 of x from 2 to 5. So we see this parentheses here. That's the indication that we can't do power rule. However, we are going to go through u substitution because we see that 3x. It's not just f of x, it's f of 3x. We know there's going to be some leftover coming out of that 3x. So go through u substitution. And we know lowercase f after the calculus would just rise up to be uppercase f. Right? We know that this is true. Integral lowercase f from a to b is just uppercase f of b minus uppercase f of a. Right? So applying first theorem, because we know that lowercase f is sitting at the derivative level. We take the integral, it'll rise up to be uppercase f, and we can plug in the upper and lower bound. But first, let's deal with that 3x. We let our u value be 3x. du dx equals 3. dx equals du over 3. Okay, we make our substitutions. Okay, pull the 3 out in front, comes out as a 1/3. Right. Apply this formula here. So we kept track of our coefficient, which is 1/3. Now we're ready for our calculus. Lowercase f becomes uppercase f. But we're not going to deal with that b and a just yet. I want to take the antiderivative. Okay. And we got to be careful here. We got to make sure that we don't just insert the 2 and 5 in for the u, because right now there's a mismatch in variable. The 2 and 5 are in terms of x, but right now our antiderivative is in terms of u. So we can just bring the original variable back. And now we can safely work in the bounds. Okay, so you have two options. Either you bring your original variable back, or you convert the bounds in terms of u. So you can insert the 2 and the 5 into the x, get the u variable version of those bounds, and then you can stay at u and then go from 6 to 10, same thing. Okay, upper bound first. Sorry, 6 to 15. Okay, 5 in for x, 3 times 5 is 15. Insert lower bound into x, 3 times 2 is 6. All right, this is as far as we need to go because it matches our answer choice E. So we can stop here and end the problem. Okay, average value. So I'm thinking average value theorem. Let's go through all the work. A and B are 0 and 4. Our function is e to the 3x. Okay, we'll take our time through this. I'm going to leave the 1/4 until the very end. I'll take the indefinite integral of e to the 3x first, but first I have to go through u substitution. So I'll go through u substitution, get all that cleaned up, take the antiderivative, then work in the bounds, and then I can work in the 1/4. E to the u becomes e to the u times u prime. Oh, my bad, my bad. I did too much here. My u value is not e to 3x. My u value is just 3x. Backtrack here. If I did e to 3x is too much, it'll give me a derivative where I don't have a matching pair to cancel out. Okay, u equals 3x, derivative is just 3, solve for dx, dx equals du over 3. One-fourth is sitting out here already. I'm going to push that 3 out in front as well, which gives me 1/12. All right, so we have a nice clean integral rule here. Integral of e to the u is just e to the u. Now that we have completed our calculus step, we can, or our antiderivative step, we can bring the original variable back. And now I can safely work in the bounds. Okay, upper bound first, 4 in for x. Lower bound next, 0 in for x. Now careful, I think the tendency is when we see 0, we just assume that everything will go away. But in this case, you see that 0 is not going to go in the x of the base, it's going in the exponents. So when it goes in the exponents, there's still something left over a little bit, right? So 3x goes to 0, but e to the 0 is not 0. E to the 0 is 1. 1 times 1/12 is still 1/12, so there's still that 1/12 left over. Okay, trying to match it with one of my answer choices here. I can just see that there's a common denominator. Okay, questions there? Number 9, find the solution to the differential equation. So we know our process here, cross multiply, separate the variables, take the antiderivative, plus c shows up, plug in the order pair, get that c value, and then see if we can solve for y. Okay, cross product, just to get things started. So once I've cross multiplied and got my dy dx in place, I realize I already have full separation, right? There's no coefficient that I need to move to the right side. My y's are together, my x's are together. So I'm ready to look at antiderivative rules here. Okay, no u substitution needed. E to the y is just e to the y, just like e to the u is e to the u. Sine becomes negative cosine. Let's see. It's up to you what you want to do. Either you can solve for C now, or you can wait until the end. I feel like maybe it's a little bit easier now before the natural log shows up. So I'm going to just go ahead and solve for C here. So I'm going to substitute in pi over 4, 0. Pi over 4 in for x and 0 in for y. E to the 0 is 1. Cosine of pi over 4 is negative root 2 over 2. Solve for C. Um, 1 plus root 2 over 2. All right, so it's a messy C value, but I'm going to take this and insert into where I started making my substitution. And let's see what we have. Okay. So we brought everything up to the function level. We got our C resolved. The only thing left is how can I get Y by itself? Okay, so we know that we can undo exponential function E by involving its inverse. So why don't we take the natural log of both sides? Okay, power property, we can bring that exponent down, bring that Y down. And then Y natural log of E, we know natural log of E just becomes 1. So there's our answer here. Okay, last page here. All right, number 10, we see a definite integral problem, but we know that with definite integral, we always do with the bounds last, right? We always got to take care of the calculus before we do anything with involving the bounds. Remember, our first option is always power rule, right? Can we expand our way through? Just because you see parentheses, don't let u substitution be your first option, right? We always want to see if we can apply power rule or expansion first. And I think that's what we can do here. This is not complicated enough for us to have to go through u substitution because there's nothing preventing us from distributing and combining everything and separating everything. So, okay. We only do u substitution if we've realized that power rule expansion is too either cumbersome or too difficult to apply. Then we go to a more complicated. But just to make sure that we understand that we can't always jump to use substitution because use substitution doesn't always work, right? If a problem is meant for expansion power rule, we got to use that method. It's not, use substitution is not the method that will catch everything in case, even if it's meant to be used for a different rule. Okay, so this is meant to be an expansion using power rule. So to expand, I got to distribute. To distribute, I first need to convert that radical to a rational exponent. Okay, distribute the x through. 1/2 plus 2. Add fractions here. 4 over 2 plus 1/2 is 5/2. 1 plus 1/2 is 3/2. So we got rid of the parentheses, we got rid of the radical, everything is nice and separated. We can apply power rule here. Add a 1 to each of the exponents. We don't do plus C because we have bounds. Do some cleanup, and then we can work the bounds in. Okay, go from 0 to 1. Upper bound first. Okay, took care of my upper bound, minus big parentheses, lower bound. Okay, so 0 and for the x's. The x's are all sitting at the base level, so it's gonna just, everything will go away to be 0 here in this case. Okay, use our calculator to do our finishing touches here. Okay, number 11, if the region enclosed by the y-axis, the line y equals 2 and the curve y equals square root of x, revolves around the y-axis, find the volume. So anytime I see the word revolving, I know this is either disk or washer, but we need to see if there's a gap. All right, so let's draw the graph. Y equals square root of x. It's like this. Y equals 2, somewhere here. And y-axis, okay? So there's our shaded region. Okay, rotating around y-axis. Okay, so we look at our dotted line, we look at our shaded region, and we see there's no gap, right? It's a flat surface up against a vertical line. If there's no gap, we don't need washer method. All we need is this method. Okay, we have to build one radius, but we see that the radius is built horizontally. So that's also a little bit of a, make sure that we remember that usually if we see a horizontal radius, we know that there's some additional work ahead of us. We got to potentially rewrite our equation because the equation that's given to us is most likely not in the correct form. We got to get this, if it's right minus left, we got to do everything in terms of y. So we got to solve for x. So square both sides, solve for x equals y squared. So that is the curve. Okay, so this method, right minus left, here's our volume formula. Okay, but let's build our radius first. Our radius is right minus left. So right endpoint of my radius is touching the curve. So that's y squared minus the left endpoint is sitting at the 0. So y squared minus 0. Our bound is from lowest to highest y value. So lowest y value is 0, highest y value is 2. Big radius squared. Okay, now we just have to work this through here. So y squared is y to the 4th. Do power rule, y to the 4th becomes y to the 5th. Work in the bounds, no need for use substitution, so no need to bring any variable back. Upper bound first, 2 to the 5th. Minus 0 to the 5th. That's just 0, 32 over 5, and then don't forget about the pi in front. Okay, number 12. Y equals x squared, x equals 4 and the x-axis. And also rotate it about the y-axis. So here's y equals x squared, parabola, x equals 4. That's a vertical line over here. And the x-axis, okay? So this is my shaded region. Okay, got the parabola, got the line x equals 4, and the horizontal line x-axis. Taking that shaded region, we're rotating around my new center. My center is the y-axis. That's my axis of revolution. So we see that there's obviously a gap, right? We see all this gap here. So we know that it's going to be a washer method. Which means we need to draw two radius. One radius, both radius has to start from the center. This is the new center, so I got to extend out to both my boundaries here. So from the center, from my axis to my furthest boundary here. That's big R. And then small little r is from the axis of revolution to the closer boundary. Again, we see horizontal radius. If we see horizontal radius, we have to adjust our equation most likely. Not suitable as y equals x squared. We got to solve for x. So square root both sides. Okay, so that's talking about the curve here. Okay, here's our volume formula for washer method. Big radius squared minus little radius squared. Okay, let's build our radius. Big R, right minus left. Right endpoint of my big radius is sitting at the 4. Is x equals 4 here. Left endpoint of my radius sitting at the x equals 0. So 4 minus 0, which is 4. Right, little radius, right minus left, right endpoint of my little radius is sitting at the curve, which is square root of y. I adapted it for the form that I need. Minus left endpoint of my little radius is sitting at the y-axis, which is equation x equals 0. And our bound will extend from 0 to however high that intersection is, right? So that intersection, we know it's going to be where the y equals x squared meets the line x equals 4. So if I just simply insert 4 in for x, I get y equals 4 squared, which is 16. So I know that I can always find any y value by inserting my boundary into the curve, right? We could also plug 4 in here and solve for y. Either way, it just feels a little bit easier to plug into the original equation. So y equals 16. So my lowest y value is 0. My highest y value is 16. Okay, big radius squared minus little radius squared. Make the calculator do the work for us there. Leave the pi out of the calculator. We get 128, and we'll attach pi at the end. Okay, pizza heated to a temperature of 475 degrees is taken out of the oven and placed in 105-degree room at t equals 0 minutes. Temperature of the pizza is changing at a rate of negative 256. So think of this as your derivative, or your p prime, because you see rate here. To the nearest degree, what is the temperature of the pizza at 9 minutes? So this kind of has this final value equals initial plus displacement feel to it. So we know initially the temperature is at 475. The temperature of the room is really not going to factor into our problem. It's not going to mean anything for us. But we know this idea, right? We know this formula here. Any final value we're looking for, we just need a starting point, whatever point is given to us. And then we just figure out the gap that exists between my starting and my ending point. So I'm looking for the pizza's temperature at 9 minutes. I know my pizza's temperature at 0 minutes. And then I also know the formula that gives me the rate of change. So I can accumulate that change in temperature if I take the integral of p prime. And then we'll make the calculator do the work for us here. Okay, P of 0, we're starting at 475 degrees. And then make the calculator figure out what is the change in temperature that's going to occur between 0 and 9 minutes. And we plug this in the calculator, we see that the temperature is going to drop 365 degrees in that 9-minute period. So then 9 minutes later, 475 minus 365. be at 110 degrees. All right, any questions? Okay. I encourage you guys to also look through pages 9 through 14. All right, these are all integral topics as well, so look through them. A lot of it is just repeated, but it's good to just to see as much examples as possible before the test. All right, if no questions, I will see you guys in class. Thanks.